Welcome everybody, and thank you for your attendance today to the STEAM in Practice. This is our first, go at running a series like this, and so we're really looking forward to your feedback as we will continue to run these sessions.
I'm Linda Galligan, and I'm I'm in the maths department at the university, so I'm the discipline coordinator for maths and stats. But you know, I have had such a long association with education. I tend to think of myself as a maths educator. That was me. My PhD was in maths education in the tertiary level. I also do lots of PD for teachers at different times, and high interest in maths modelling, particularly for in the school area, and bridging that into the university and then into careers. We have an applied maths degree here and stats, so a lot of the people I can call upon can tell me where they use maths in all sorts of interesting places. So we've got a maths modelling workshop coming up at the end of the year, and we've got international people coming to talk to us about things that I don't even understand, but it's all about maths modelling. And we've got a PD for teachers on at that time as well in November. So I'll talk a little bit more about that later on. But I'll stop talking now. You know a little bit about my ability in Chinese as well. So
that was something new that I learnt this afternoon, so that was good. So I'm Tanya Leach. I've been a teacher for over 20 years in a range of contexts at CathEd and Education Queensland, spending the majority of my time in rural and remote locations, in state STEM position, one of 7 STEM champions, as a maths regional project officer, and a number of other roles. And I worked with Josie in one of my contexts.
Okay.
Yeah, so which is lovely. So I'm now at the university as a lecturer in curriculum and pedagogy in primary, secondary, and in the Masters of Teaching and Learning. And my passion really is about ensuring that learning for students is connected to the real world, and that we get students to move beyond just, getting the right answer in the test or the assignment, but really developing a deep understanding of learning. So as we move forward today, let's just review the session intent. So we are using STEAM, not STEM, as a learning context. And what we wanted to do is just forefront that we're really looking at it as an integrated approach for a way of accessing those higher order thinking skills or 21st century skills of critical thinking, creativity, collaboration and communication. So today we're just going to position that, because throughout the other workshops you'll dive into some deeper or alternate opportunities to explore that. And really we want to lay the foundation from where it sits in the curriculum and what it can look like from a maths perspective. So we're going to look at the role of critical thinking in maths. We're going to explore 2 practical strategies and get you to have a go at creating and engaging in those strategies, and then also have a reflection on where then critical thinking sits in the context of STEAM. So to begin, and as many people know, all workshops are interactive, and so our first activity is to get you to activate your prior knowledge of what is critical thinking. So I'm just going to ask you to think about or visualise what you believe is critical thinking, and in the chat box just start to type down. It might be what you see kids doing or how you might define critical thinking. I'm just going to pop that in the chat box and then we'll come together to talk about that. So I'll give you a minute. Okay, so we've got some behaviours coming through there and a definition of thinking for yourself, so not just regurgitating known definitions in familiar contexts, but perhaps applying it into alternative contexts through that word transfer. Yeah, new or different ways than what they're used to. So sometimes it's about bringing together, or identifying the knowledges and the ideas that you need to have. It's defending positions and ideas using evidence. And it's drawing on all those learnt knowledges to be able to do that.
It might look differently depending on the classroom and the, like, primary or secondary, or even the type of classroom you're in. What does critical thinking look like in a maths classroom versus critical thinking in an English classroom?
Absolutely. And so to pull together then our thoughts, and we're really on the same page there. When we look at how to critically think, there is Richard Paul was one of the, big researchers into critical thinking that went across multiple contexts, and not just in education but in engineering, etc. And he's collaborated since the 80s really to unpack the role of critical thinking and what that looks like. So his definition is that the thinking that emerges as you think critically is clear, accurate, knowledgeable, reflective, and fair in deciding what to do, what you believe, or what to do. And so there's a couple of different models that he's developed over his work. One of them's on the right, and it looks at some of those dimensions of critical thinking. And we do have references at the end of this session, so if you do want to go in and have a look at his work, please do. But a simple Google Scholar search will also reveal some of his research as well. So he really looks at different meaning-making systems and how they come together. So when we think about your definitions, about thinking differently, bringing ideas together, we can start to then look more specifically at some of the dimensions within critical thinking. So you have a point of view, there's a purpose, and so STEAM can certainly be that context or that purpose. You have concepts and ideas, and you actually talk about your assumptions as part of your informing frame. And then you also come to some logical assumptions as well. So when you do it, you have to be able to gather information. So as we're going through this, start to think about what that might look like in an education context. You need to make inferences, justifiable assumptions, so connecting those ideas together. And also, really importantly, checking your information for accuracy and being able to defend your position. So that's some broader research. When we look at then how are those ideas then reflected in the Australian curriculum, and this is really important because we know that as educators, this is our core business to implement the Australian curriculum. So this is the definition that sits in there. Critical thinking is at the core of most intellectual activity. It involves student learning to recognise or develop an argument, so similar to Paul's definition, using evidence to support that, draw reasoned conclusions, and use information to solve problems. So we can see the thread of your ideas coming through with some more specificity through Richard Paul's definition and then into the Australian curriculum perspective. So it sits within the general capabilities, and we incorporate those into our teaching as we do that. And you can see there the skills in the diagram. Now, critical thinking sits or is housed with creative thinking within the general capability as well. So it's important to acknowledge that. So it's one thing to be able to talk about what we say it is, and what students might need to do or produce when they're critically thinking. But it's another thing to be able to really have clarity around what that looks like in the classroom. So to begin to develop that picture, what we're going to do is unpack from a curriculum perspective what this looks like in the learning areas of science, technology, the arts and maths. Now, I know we don't have everybody here, but I did pre-populate and allocate you a learning area to look at. So what I'm going to do, so just have a look at your name. What I'm going to do shortly after I explain this short activity is I'm going to give a link into the chat box where you're going to access the section of the general capabilities that says what does critical and creative thinking look like in these areas, and your task will be just to look at that one learning area. We then have a shared document which will look like down here on the right. And what I want you to do is to be able to populate your ideas, just the key verbs that you see in the learning area that you're looking at. We're then going to look holistically to have a look at those common aspects for a STEAM lens. So first of all, I want to make sure that we understand what it looks like when I'm asking you to annotate, because this is sometimes a new platform for some people. So when I slide across to this sheet that you can see there, I'm going to get you to either hover across or down, and you might see a menu like the one here, where it will then have the option to annotate. Once you click on annotate, you'll have a little menu. If you're using an iPad, you'll have a little drawing icon, and you click on that and this menu pops up. And then I want you to select on text, which will allow you then to type into any box. If you want to move anything that you've said, please click on the select and just drag and move across. Does anyone have any questions around what we're asking you to do? I'll just find your one area, find the verbs.
Where do you find that area, Tanya?
In the link. So go down. Have you opened the link in the chat box?
Yeah, I've opened the link.
Scroll down.
Critical and creative thinking.
Yep, I open that up.
Yep. And I've got a big that thing, creative.
Scroll down. Yep. Scroll down and you'll see the headings of your learning area. So when we have a look at the definition of critical thinking coming down into the Australian curriculum to have clarity and be able to defend and reason, and if we're looking at STEAM as a context, we want to look at holistically the common aspects of critical thinking.
Mass.
Thanks, Coco. We'll see you when you come back on. And so if we have a look across the science, technology, arts and maths as it sits there, just, yell out, what are some of the common critical thinking attributes that you see?
Evaluating.
Yeah, evaluating's there.
Analysing.
Yeah, I see a lot of analysing and from different perspectives as well. So in technology, you're analysing problems. In the arts, motivation and influencing factors.
But you could move them around. Like you could put anyone in any corner and it'd work.
It would.
I think, yeah.
And although there's some specificity in each learning area about, the ways in which you might do that because it's housed within a specific context, there is a strong feeling there that the students need specific skills to be able to think critically or use those 21st century skills to be successful within each discipline area. And then if you're looking at a STEAM context as an integrated unit, the critical thinking can be, that thread that you pull through, and the focal point for that and the learning areas are the content and context that you create for them to be able to demonstrate these skills. So it's really important that as we move through, we're confident in our knowledge of where this sits in the Australian curriculum. We have clarity around the definition, but most importantly, we have clarity around the behaviours or the learning behaviours that we want to see from students. So when we're thinking about analysing and evaluating, well, we need to be able to scaffold that thinking and provide continuous opportunities for students in the classroom. So in that, even the one that you can see on the screen at the moment, you can see that there are specific, nested or developmental look-fors for the skills as we move through. So we know that in critical thinking we have to pose questions. So what does that look like if you're teaching foundation prep as opposed to when you're teaching the end of year 10? Can I just ask, which year levels are you teaching?
Year 5.
5, yep.
I'm 8 to 12.
8 to 12?
Yep.
I'm 5 and 6.
Yep.
5 and 6.
Yep. Perfect. Lovely. So we've got some upper primary there as well. So it's a challenge in secondary when the kids come to us and they haven't had the opportunity to be able to acquire these skills or to be able to use them independently. So this is a really important document as you're going through, particularly if you're in a school where you develop success criteria and learning intentions. Using these look-fors will really help give clarity to the students. Are there any behaviours there that you think your kids would struggle with at the moment or would be able to do comfortably?
I know in year 5, a lot of my students, when we do research, they have a lot of trouble condensing and combining information. So just in that level 4 column, going across to organise and process information.
Yeah, synthesising is certainly a higher order skill, and they need to know how to identify the main ideas and then bring that together holistically. A look at what critical thinking is. We've had a look at starting to position the important documents that you need to be really familiar with in terms of the Australian curriculum and what that means in teaching and learning. But now we want to just take a little moment to have a look at why is this important for learning? And why can we not ignore the need to include critical thinking in our everyday teaching and learning opportunities within our pure learning areas, but also in the opportunities that we might provide through a STEAM context. So for the purpose of the next part of the session, we are going to put a mathematics lens on because it's easier to dive deeply into one learning area and to look at what that means. And then we're going to helicopter that out into what that looks like in a STEAM context. So in the maths curriculum, I just wanted to forefront that the structure of each curriculum area is really important to know. And if we go down and look at the key ideas here in maths, I want to show you where creative thinking links into the learning area as well as the general capabilities and coming together. So in mathematics, in the key ideas, we have the proficiency strands: understanding, fluency, problem solving and reasoning. And these proficiency strands describe the actions. Now those actions of mathematics work together over here where it says the structure around the 3 content strands. But we're going to have a look at what happened when the Australian curriculum was first implemented, because the big ideas and proficiency strands weren't full-fronted well in the documents, but they've now been changed around to make that an important focal point for maths. So when we have a look at these key ideas and you look at the understanding, fluency, problem solving and reasoning, you'll start to see connection points between what these ideas are and critical thinking. So even in understanding, if you go along the first line to the second sentence, it's got students need to make connections between related concepts. So that was part of critical thinking. In understanding, they need to develop a relationship between why and how. That's in critical thinking. And they need to represent concepts in different ways. Okay, so that's also in critical thinking. When they're fluent or they're developing fluency, they learn to, if we go to the second line, about a third of the way across, they recognise robust ways of answering questions. So they choose different ways. They can talk about the solutions and the ways of working, and they start to identify what are the most efficient ways. Problem solving, of course, they need to make choices, design their own investigations. So do we give opportunities for students to do that, to question the environment and bring those questions in, unpack them and learn? And reasoning, do they have a meta language that they can use to be able to talk about what they're seeing, what they're finding, what they're using? So within the learning area, within the structure of this learning area, you can see the alignment to the definition of critical thinking. So if we know critical thinking is important, then again, why do we need to bring a focus point to it? One of the writers, Dr. Peter Sullivan, did a desktop analysis of the implementation of the Australian curriculum after about the 2nd or 3rd year. And what he found was that the verbs were missing in most teaching, and teachers tended to skip over looking at the structure of the Australian curriculum and went straight to the content descriptors. And the content descriptors, these verbs were integrated into them but were not explicitly stated. So teachers' interpretation became very content and fluent based. So we need to look at putting those verbs at the forefront, and the way to do that is to collaborate and come up with meaningful contexts for students to plan with, or to plan with the students and let them develop areas. And we need to incorporate problem solving. Why then, from a national and school perspective in terms of learning, is this also important? If we look at adult learning, and this was 2012, we're waiting for the new data to come out, there is an international survey that's conducted, and 25-year-old, no, actually it might be 18-year-olds, sorry, to 65-year-olds are included. That yellow line there, that says that that's where everyday mathematic concepts sit. So to function on an everyday level, to do a budget, to fill your car up, those sorts of things, to go shopping, we need to have a level 3 knowledge base and application. But you can see there that we have a significant number, according to this survey, of our population that sit below that. So in our society, we do not have strong numeracy skills. But what does that look like? So I said we needed a level 3. Here's an example level 2 question. And so we can see there, it's a fuel tank. And the question is, this fuel tank holds 48 litres. How many litres remain in the tank? Now, this was an estimation question. And so there were a whole lot of responses that were, that were considered correct in there. But from that, the survey indicated that 3 million Australians would not be able to answer that question. And so that's quite alarming when you think about it. And there's a number of reasons. There's literacy involved and interpretation. But if I get you guys to have a look at that question, what would be your immediate response to that? You can either type it in the chat box or yell it out.
So 3/4?
Mm-hmm. Yep, so you could say 3/4.
Yeah.
What else could you say?
36. Mm-hmm.
Yeah.
I'm looking at the chat box, so I'll...
Oh, good, thank you, because I can't see it. Yeah. 36. Oh, every time I click the chat box, it moves forward.
That's okay, I've got, no,
Thanks,
leave.
Linda. Yep, 36. Now, if I ask you, so they accepted anything above 28 and below 46 as a response if you were giving an answer. And I don't know if they accepted 3/4.
Yeah.
What did you do to solve that? What thinking did you do? So for you, Josie, when you said 3/4,
Yeah,
how
I was
did you come up with that?
just looking.
Just looking, okay.
Yeah.
So you activated some knowledge around fractions or visual representations?
Yeah.
Great. What about getting 36? How might some of the thinking been around that?
Hi, Tanya. That was Amanda here. How are you, Tanya?
Hi, Amanda. Good.
My thinking for the 36 was half of 48 and then half again and added them together.
Perfect. Okay, so that's another way. What's another way? What else?
I probably looked at 3/4 first and then thought, well, what's 3/4 of the 48?
Mm-hmm. And did you do that 3/4 of 48 equation in your head, or did you go?
No, so I would have said the whole is 48, take a quarter.
Yeah. So
get to the
did you divide by 4 and then take that away?
Yes, I probably would have, yeah.
Yeah. So when we teach that in maths, if we were looking at teaching it in the most efficient way, knowing 3/4 and being able to do 3/4, saying 75% of that or whatever it is the most efficient way on paper. But what we know is that most people go half multiplied by 3, or they go half and add the first half and the second half, which is a quarter, together. They rarely do the whole, take away a quarter, so which is interesting. So as we're teaching mathematics, just doing a simple exercise like we've just done there to say, what was your thinking? You know, and valuing everybody's thinking and everybody's pathway enables you to all of a sudden value that there are different ideas and different ways of solving problems, no matter how simple they are. And that's something that in recent studies of classroom practice and pedagogy is missing in our current climate. And there's for a number of reasons there, and I won't go into that. So it's alarming that we have a lot of adults who cannot answer that question. When we look at our students then, we know, and you would have seen in the news, I haven't added in the latest data here, but there are 65 countries who engage in the PISA research, and we are one of only 4 that have been in constant decline. Regardless of where we're ranked, and our ranking is quite okay, but we are constantly going backwards. But the thing that gets me, I'm a mum of 4 kids, is that we are 4th highest for an increase in maths anxiety. So I asked myself, our results are going down, but our kids are becoming more anxious around maths. Why? Our adults are becoming less numerate. Why? What's happening here? And there's a number of factors, and we're just going to look at the education factor. When we then started to marry the pieces together, so we started looking at what's happening with student learning, what's happening with adult numeracy rates. We then looked at, well, what's happening with teacher understanding and practice in the classroom. And when the Australian curriculum implementation came in, as I said, we defaulted to looking at content descriptors and implementing it, and it was very fast paced. There's quite a lot of pressure to get through different things. And what happened was a lot of that lovely conversation, the inquiry and the valuing different thinking sort of fell away from our classrooms. So we asked teachers, hundreds of teachers, we gave them a Year 3 content descriptor around multiplication, and we said, if you had to find out what students were thinking or knowing about this, what questions would you ask? And these were the questions that they put up: single digit, double digit, and what they called a problem. What we found from analysing this was that this was typical, and students, when they're doing these types of questions against the proficiency strands, had limited opportunities to actually develop fluency or to really test their understanding, reasoning and problem solving. Questions like this really just ask them to recall facts or a learnt procedure in a known context. There's multiplication up the top. They give an answer, but we don't actually know if they understand what they're writing, the quantities, or what they would use. The other part about that was that many of the problems are actually exercises. So the problem down the bottom there said there were 350 students. They spent $15 at a disco. How much money did they make? So there was confusion around what was a problem. The research that went along with this, Judy Anderson and the Australian curriculum, unpacked every content descriptor and showed that when using the proficiency strands, there are multiple ways of students demonstrating their knowledge, from being able to use digital technologies to collaborating to verbalising to representing in a number of different ways. And that's really the point we want to make there, that there are multiple pathways to demonstrate your learning. And when we're valuing critical thinking, that's what we want to see in the classroom. So let's have a look at the difference between quality questions. If you write down the 4 digits, 4, 2, 6 and 7, I would like you to put into the chat box a question. Now, this is a common question used to test place value. So with those digits, using each digit once, can you please write the largest 4-digit whole number that you can? Off you go. So what is the largest 4-digit whole number using each digit once? So just type it in, or if you want to call it out, please call it out. Yep. So using each, it would be if you could use Coco each, if you could use each digit and repeat it, but just using the 7 once, the 6 once, the 4 once.
2 people got 7642. Can you see that?
I can now, thanks. So that's correct. I want you to think about now, what is the knowledge or processes that you had to activate to get that answer? And just call that out. What did you need to know to be correct?
So I had to know the order of the digits from least to biggest, or biggest to least, however you depend on saying it. But I also had to have an understanding of the different houses of place value and whether they run from left to right or from right to left. And with that, you know, you have your knowledge of your ones, your tens, your hundreds and thousands. And so you need to order from there. But like you say, when you order, you have to know if you're going left to right or right to left in order of.
That's right. So you need to know the way numbers were written. If this was something that was practiced in a classroom, so they, you know, did this as a warm-up, do you think you would actually have to know place value to be successful? Or would you just need to know how to order and that you wrote from left to right?
No, you need to know place value, definitely.
I'm going to challenge that.
Oh, now I'm not sure, because I feel like they could.
You might know it, but if I got a student to do that, could I know definitely that that's place value? You would assume that they would, but they might not.
Yeah, no, you can make a good point.
So now here's another question. So again, using each digit once and writing a whole number, I want you to write the third largest whole number that you can.
Cool.
And I'm going to get you to stop. Doesn't matter if you don't complete and put the number down. What I want to ask you is, what was your thinking process? And how is that different to the first time?
So you had to know place value to be able to do that.
So one of the largest mistakes that even adults make when they do this is they go to the 4 first, and kids do that. Because they're defaulting to ordering numbers, and then they go, oh, hang on a second, that's not right. And they start to think 7, 6, but what can I move the 6 and the 4 around? What else can I move around? And start to unpack that. So simple question, but different. And knowing what behaviours you want to see from kids allows you to ask the right questions. Now, when we start to look at that, and it's important that I should say that when you are asking those questions, that the students must be able to share and articulate how they solved it, because that reasoning enables kids meta language and confidence in critical thinking and problem solving to emerge. So the first one there, when we look at that, it only enabled us to look at recalling facts and knowledge in that fluency. But the third one there could have helped us connect related ideas, maybe to communicate if we asked in the reasoning part, and also verify if our answers are reasonable. So we asked this to kids. We wanted to see, well, could kids do it? And these are the results. So we saw that Year 3 students, and there were 500 students, the first question, 92% could get it and 98. The second question, 42 and 57. We thought, what's going on here? So then we went to Year 9 students and we asked them similar questions, going from like a fluency or a procedure question on the left, a conceptual open-ended question, and then also a problem-solving reasoning question. And you could see that there's 4 different schools there, and the rates drop significantly. Okay, the procedure, they're quite confident. The open-ended question, it drops a little bit, but the problem-solving reasoning, we're having major difficulties with. We then asked more Year 3 students, and we did the same, procedural, conceptual problem solving. And we can see the red question, yellow question, green question, same trend. So what that affirmed for us was that our teaching was very good at getting kids to be able to get the right answer in familiar context, but the ability to transfer and reason and use their meta language was not so strong. And part of that, just before I transition to Linda, was that there was a study done then of pedagogy, and it compared some of the top performing countries to Australia. And what it found was that in Singapore and Japan, only less than 50% of pedagogy was spent explicitly teaching, The rest was spent in collaborative problem-solving opportunities where then they would then unpack their solutions, justify and reason and question other groups. In Australia, 95% of our classroom teaching is spent on explicit teaching, and some classrooms there's no problem solving, or it's an add-on as one opportunity, maybe once a week, or as an assessment piece. So when we start to look at those huge contrasts there, it really puts the case forward for critical thinking being that integral part of all learning. And so how do we provide those opportunities to students? So I'm just going to hand to Linda.
So I know we've only got about half an hour left, but we do want to spend a bit of this time talking about some examples of where we can get this critical thinking really into the classroom. And you've probably heard about inquiry-based learning, and I won't go into it a lot. Judy Anderson, again, has written quite a bit about this. And there's a big continuum on what it can be, from problem solving up to mathematical modelling. And in mathematical modelling is where we use a lot of that at university and in industry, where we're really describing a system in the real world, whether it be climate change or dust modelling or looking at waves, or so many different examples of modelling. But we're trying to encourage students to start thinking that way from quite an early age. And there's different approaches to it. So you can take a student-centred teaching approach or a teacher-centred teaching approach. You can use cooperative learning, all those words. But I think as a teacher, you sort of know when you're doing it. You know, you're asking students interesting stuff. So I just thought do you guys know Dan Meyer at all?
No.
Oh, listen, awesome. There's a YouTube. Just Google Dan Meyer. I'm going to see if I can I share the screen and also the video, Tanya? Does that, I think there's something on the screen that gets you to...
Can you share your screen? The green box?
Yeah, just, what's happened here? It's gone to share screen. Yes, and I want to share my... So can you all see now a Dan Meyer TEDx
Yes.
screen? Yep. So we'll try, this is just halfway through, and see if we can get...
For a second, Einstein, who I believe has paid his dues, he talked about the formulation of a problem being so incredibly important. And yet, in my practice, in the US here, we just give the problem to the student. We don't involve them in the formulation of the problem. So 90% of what I do with my 5 hours of prep time per week is to take fairly compelling elements of problems like this from my textbook and rebuild them in a way that supports math reasoning and patient problem solving. And here's how it works. I like this question. It's about a water tank. The question is, how long will it take you to fill it up, okay? First things first, we eliminate all the sub-steps. Students have to develop those. They have to formulate those. And then notice that all the information written on there is stuff you'll need. None of it's a distractor, so we lose that. Students need to decide, all right, well, does the height matter? Does the side length matter? Does the color of the valve matter? What matters here? It's such an underrepresented question in math curriculum. So now we have a water tank. How long will it take you to fill it up? And that's it. And because this is the 21st century, and we would love to talk about the real world on its own terms, not in terms of line art or clip art that you so often see in textbooks, we go out and we take a picture of it. So now we have the real deal. How long will it take it to fill it up? And then even better is we take a video of someone filling it up. And it's filling up slowly, agonizingly slowly. It's tedious. Students are looking at their watches, rolling their eyes, and they're all wondering at some point or another, man, how long is it going to take to fill up?
Oh, no, again!
Okay.
Sorry.
That's how you know.
Sorry, guys.
Right?
I was talking to my lady. Sorry.
I just thought I'd show you that little clip from Dan Meyer. He's got an awesome blog about a lot of this open-ended questioning and how you take away all that scaffolding and let them start playing themselves. So, Tanya, are we back to you again, or?
Yeah, just quickly.
Yep.
Perfect. So if we take that idea of providing opportunities for students, then there's a couple of really simple ways. So you don't want to just throw kids straight into this if they aren't used to it already, because often that's when it then fails and then we give up and the kids give up. So we need to think of ways of stepping this in and building our confidence and the kids' confidence. The first thing is to ensure that we know that a question that tests mastery is an exercise. So we have to look critically at the resources that we're using to go, are we giving kids exercises that just really test the mastery of a procedure, or are we giving them opportunity to solve problems? Now, in my classrooms, I love to have a box for fast finishers, and their job was to actually create problems. And we would have a whole problem-solving section where kids would challenge each other to come up with really alternate ways of thinking and to be able to come up with different solutions. And then we'd have times where we'd come together and critically analyse and look at which were the best solutions and why. So really simple techniques to use. But let's have a look at what it looks like in the classroom. Here's a very short video of one teacher talking about how she does it with kids and what that does for their learning.
And learning about dividing fractions, and it was actually fairly easy for the students to start just inverting and multiplying. That was very easy, but I didn't think they had a very good understanding of what dividing fractions actually was. So I tried to devise a lesson that would allow them to go through all of the steps and prove their algorithm. Now, to do the algorithm, that's the easy way, isn't it? But we want to really think about this in a different way. We want to be able to create something that will prove the algorithm. Developing a problem, taking it into kind of a story, and then taking it to the next step, making a three-dimensional model.
Then I divided it into 7 eighths, and then I took an eighth away from the 8 to make 7. Now I'm working on 4.
I actually really enjoy making 3D dimensional shapes. Then you can see the problem. It's not so flat. You can see what it looks like under it or over it. You can touch it. You can feel what it would actually feel like if in real life.
4s, and then we'll use this one to make it 8s.
In a classroom that supports higher order thinking skills and supports the learning and teaching of those skills, it is not going to be a quiet, worksheet-oriented classroom. It is frequently noisy. Children love sharing their ideas with one another.
I like being able to show my math because then they would know what I got and then how I got it, and then they would know if I got it right or wrong.
Because it would add too much. And then these go in between.
It's important for the students to ask questions to test to see if they can back up their answer and defend it, other than knowing that they just did it and they can't state it so that they really know it.
They were able to discuss with one another. They had to analyze each other's ideas. They had to prove to each other that their vision, their model was correct.
Cut it in half. How do you know it's 3/8?
Because right here,
Higher order thinking skills are imperative for children to learn if they're going to be successful academically, socially, in the job market.
I understood it better by creation. I could create stuff with my clay. Evaluating, the teacher asked us to defend our problem. And understanding, my partner and I had different solutions of doing the problem, and we both learned a new way.
So it's just really nice, I think, to be able to have a look at it in practice and look at collaborative work, but you can imagine that you need to set up some structures and some boundaries around that. Every child was on task. They, had accountability for their learning, but clearly they hadn't just been thrown, here's some Play-Doh, make a 3D model. They'd actually learnt those skills prior to that. One of the ways is to simply incorporate an open-ended question into the beginning or the end of a lesson to start that dialogue and to start the sharing of practice. And we can do it in non-threatening ways. So first of all, we can start to think individually and just share in pairs, and the teacher can just walk around, look around, talk around. Then we can grow into sharing in front of class or having, a wall where our competition is to come up with as many different ways of solving a problem. So in an open-ended question, again, requires more than remembering a skill. You learn from each other by answering the questions, and there's several acceptable answers. And you have to defend, evaluate, and analyse, use that critical thinking. So again, the answer is 5 apples. What might the question be? Very simple, open-ended question. One way of doing it is to identify a topic, think of a closed question and write it down, and then use the answer to develop an open-ended question. So if I go down here, I can have a look. I've got identify topic, so there's shape. Think of a question, what is a square? And then create a question around that, so maybe using the answer. To have a question that provides not an immediate response. So it might be, how many things can you write about a square? Another one, addition. Think of a standard question, 337 plus 241. So instead of just giving an algorithm, it could be, I spilt, not I split, but I spilt. Numbers disappeared. What might those numbers be? And so, students really have to be able to, like that 4267, the third highest number, they have to really stop and think about what they're doing, activate knowledge, defend, justify, because it's not just, the answer is 6. Who got that right? Tick. But it's about, show me how you know and what are you thinking. And we're developing that confidence to then be able to apply that across learning areas and in an integrated area. So we've got a couple of questions there on the screen. The topic is time. What is the time shown on this clock? What might be a open-ended question that you might write instead of what is the time shown on this clock? What's something you might write? And you can just pop that in the chat box instead of annotating it. So I don't have to get rid of all of it, and I'll get Linda to monitor it. One that I'm thinking of might be, what's your favourite time of the day and why? Draw this on a clock. Now, it's still closed for an individual, but across the classroom, there's multiple answers, and then you start to get comfortable talking about your choice and why. What might be another one?
So what time do you go to bed?
Yep, perfect. Okay. So when we think about
this one, what 2 times are 35 minutes apart?
Yeah, good. So we can move it up. And often that's a really good one. That's one that's often shown in transferring into unfamiliar context, because they have to really think about 2 times and the relationship between the clock. So then there's another way of also developing open-ended questions, and that is identifying a topic, thinking of an answer and creating a question. I find this the easiest way. So again, I might have area. The answer might be 6 centimetres squared, but my question is, how many triangles can you draw with the area of 6 centimetres? Yeah. Or counting, the answer might be 4 in a lower primary classroom. I counted something in our room, there were exactly 4, what might I have counted? Or fractions, 3.5. 2 numbers are multiplied to give 3.5, what might the numbers be? So you really have to have deep understanding and fluency to be able to answer these questions. And as a teacher, not only is it teaching kids how to utilise their knowledge in a more meaningful and exciting way, but it's also giving us valuable information as to whether our kids are stuck in fluency or actually have a deep knowledge. It can reveal misconceptions. So let's think of one about money and 35 cents, and then I'll hand over to Linda. What's a question we can come up with if the answer is 35 cents?
How many ways, this would be for lower primary, you could say,
Yep.
how many ways could you make 35 cents using different coins?
Perfect. Yep.
A question where the change was 35 cents. So I went into a shop with $10 and I got 35 cents change. How much did I spend?
Yep. Or what items did I buy?
Yep, something like that.
Yep.
Would you be happy with 35 cents pocket money?
I would have back in the 70s.
They bought an awful lot back then.
Yeah, it certainly did. So very simple ways of just starting and going, okay, guys, you know, you've got a topic. You can pull these off the top of your head. You could use a question that you already used in class that day and then just make it open-ended and get to do it. One that I love doing is, you know, like circles with fractions. And often you get them to identify a half or whatever. But I say, how many different patterns can you make if half of it is white, you know, a quarter is red and the rest is blue? And they'll often block it out, but then they'll actually start to divide up the fractions into, you know, smaller fractional parts. And so it's really makes them extend their thinking. Okay. So the other way is through a Fermi problem, and I'm going to hand over to Linda to talk about that.
Okay. So when I say the word Fermi problems, have you heard of it before?
No.
No.
Oh, excellent. It's all new. That's good. Well, you can go Google it and you can find out lots more about it. But it's these sort of problems that if I pose a problem to you, you go, oh, yeah, I can solve this sort of problem. And you can, on the back of an envelope and perhaps with a calculator, go, oh, yeah, let's assume blah, 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 and come up with a solution in, you know, within half an hour or a bit longer or whatever. But no, something that you can do. And it can be at really any level. So the classic example from Fermi, the original guy who did it back in, I don't know, last century, said how many piano players are in Chicago. So you can then take that one step further and go, oh, how many dentists are needed in Kingaroy or the Gold Coast or Brisbane or whatever you are. So just on that question, what are the sorts of things that a student or you might need to then ask to try and get that answer? So any ideas of what are the follow-up questions that might be discussed in the classroom?
So if you were doing the dentist in a place, you'd have to work out how many people were in there. Is that the sort of thing that you mean?
That's right. Yeah. So that would be the first one. Would be the number of people in the city. So that's number one.
Yeah.
And then you probably, and that could even be an assumption. Oh, I don't know, how many people in Toowoomba? Let's say there's 100,000. And you often take the numbers that are easy to then work with, so you don't have to use a calculator. Yeah. So you've got the number of people in Toowoomba. So then what would be the next thing you'd like? Oh, what else would we need?
How often do people go to the dentist?
Exactly. So again, you go, oh, I wonder how often. Let's say once a year. That might be pretty easy. So you've got that. And then what's the next one?
How many people do they see a day?
Yeah. So now you go, oh, okay. What is that? And then that would tell you how many people a dentist would see in a day. Yeah. So would that be 8, 7, 5? And then you just do and how many days would that be? So you multiply the 8 by the 240 and divide that into the 150,000 and get your answer. So within a relatively short period of time, you can sort of guess an answer, and you can see that you can imagine doing that in groups. And within a relatively short period of time, you're going to get some answers that are relatively similar or that aren't. Which brings me on to my next point. So, Tanya, did anyone watch Catalyst the other week with Lily at all?
No.
Oh, You guys are just too busy marking, I know, or something. So Lily Cerner, she's the letters and numbers person on SBS. She has been for a while. I've met Lily a few times, and she's a mathematician. And there's a reason why that she's on TV now. She's probably a relatively good-looking mathematician. But one of the things she did was she went up to a heap of people and says, well, what do you think the weight of Uluru is? And, people were going, I don't know. I don't remember how many numbers she collected, but she collected a lot of them over a period of time and then averaged them. And she found the average, and that average was extremely close to the estimation that, a geologist made. So it was this... the power of the crowd to be able to get answers to interesting questions. But again, with Uluru, can you think, okay, what do I need to guess the weight of Uluru?
You need to know how big it is, how big the base is.
So big...
like the
volume?
Yeah, so basically you probably need the volume.
Yeah.
And what else?
And the density?
Yeah, so, and again... How would you do that? You'd probably get a rock and go, I wonder how much that weighs. So, and again, it wouldn't take you too much. And even like from a picture, you could probably guesstimate how long it is or wide or high, or students might actually have been there.
Or they could quickly Google it.
So what was that?
They could just quickly Google it. It would be there.
Yeah. It's interesting. I don't want to sort of be too dogmatic on what a Fermi problem is. It sort of says without reference materials, but Fermi wasn't around when Google was around, so it doesn't really matter. But it's these sort of really open-ended questions on anything that can create really, really good discussions in your classroom, and anything from primary up to year 12, and in fact in university. So, how are we going? Well, we're almost out of time. So, Tanya, can you just press on to the next one? So this brings me on to the next, when it comes up. Yeah. So I've actually got a competition just started around for kids in schools, and if you've got kids from year 7 to 10, by all means, invite them to this competition. And all it is create a Fermi problem and solve it. And it's based on your local area. So who have we got? Josie, you're up at Kingaroy, aren't you?
Yeah, but I only teach up to grade 6.
Oh, yeah, okay. Well, I'm not going to let you get out of it that quickly. So think of Kingaroy. What's a Fermi problem in Kingaroy?
How many peanuts would sit in a silo?
Awesome, of course.
How many peanuts are in that field that they've planted? Like, how many peanuts would you get out of it?
Awesome. Yeah, that's good. Maddie, where are you from?
I'm on the Gold Coast, and I was just thinking of a question. I just immediately thought of that Q1 tower, and I thought, well, maybe we could get the kids, again, without Googling, because that's not the idea. It's more about the process and the thinking. Yeah. But I don't know, maybe how many jelly beans do you reckon it would take to stack up on top of each other to get, to that tallest tip of the tower? I don't know.
Yeah.
That's good.
Louise, where are you from?
I'm in the Redlands. And I was thinking maybe, strawberries. Maybe they could estimate the amount of mangroves along, the number of mangroves along the coastline or something like that.
And how Coco, are you still with us? Yes. Oh, you're muted.
Here.
Can you think of a Fermi problem, Coco?
Not at the moment.
Oh, okay. That's right. Amanda, where are we? Deborah, are you with us? No. How about Alwyn? I know you're here, Alwyn. You're in Toowoomba.
Am I?
Yeah. I can tell from the bricks.
I'm just getting ready for the handover for the next week.
No excuse. Come on.
You want to know, for example, how many footsteps there would be between USQ, Toowoomba and Springfield.
Yep.
Yep.
Oh, yeah. Mm.
And Deb's put one up. How many litres of water are in the Brisbane River?
Yeah.
Tanya, do you want to clarify that?
No.
What do you mean?
You could have in a section of the Brisbane River.
Yeah. And see, that's right.
But you said how many metres of water?
Litres.
Oh, litres.
And I think what these problems do is that you go, okay, here's the question, and quickly here's a solution, and then what you do, you go, oh, okay, how about if we then think of it again and refine it a bit more? What are the assumptions we made in the first instance? Can we refine that a little bit better to get our model a little bit more reality? So these Fermi problems really lend themselves very well to a more detailed modelling process that might take you a whole semester. Now you ask a student to go model something or other. So, but they're beautiful examples of very open-ended questions, like Dan Meyer said, is, how long does it take to fill a water tank?
So there's two really lovely ways. One where you involve students, explicitly in coming up with questions, working collaboratively, defending, evaluating, analysing, and you can certainly see how that can be in a STEAM context. To be able to do that, you might just provide a visual stimulus for them to come up with that. But the important part is then to come back and look at, well, what are those critical thinking attributes that we want to see? How are we going to scaffold that? And it might be that in the other learning areas, they scaffold and learn that first, or they learn it straight away through a STEAM context. And there's some more information. You'll get these slides sent to you around the Fermi competition. So today we've looked at position.
Oh, that's just the back of the envelope. So that's what we're going to do, is write on the back of the envelope.
Yes, we talked about it instead. So we positioned STEAM as a context. We've looked at where it sits deeply in the curriculum and the documents to come to. We looked at a really strong argument for why it's important to bring this back and forefronted in the classroom. And we looked at two very simple practical approaches for incorporating critical thinking through open-ended questions and Fermi questions. As we move into next week, there's a little video here about how you'll then take that into a more arts-focused context. So we'll just quickly watch that.
Hi, inspiring STEAM educators. This is a little appetizer for your session next week, and to help you get prepared for a couple of things that you need to have completed before you start the session. We'll have three facilitators in next week's session. First, Alwyn Powell. He's our maths educator, but his passions and his expertise go well beyond maths, as you'll see in our inspiring session. We'll also meet Steph Piper, our community engagement and makerspace facilitator, and Steph's going to take you on a quick tour of the Toowoomba facilities. And finally, myself, Katie Burke. I'm an arts educator, and my passions lie in the field of integrating the arts meaningfully across the curriculum. Next week's session, you're going to really hone in on what is the creative potential of STEAM learning and how can we draw out STEM concepts through meaningful arts engagement. So what does that even mean? Well, that's what we'll look at next week, and how we can avoid that making pretty stuff approach, which is often characteristic of how we sometimes view the arts. So this is going to be a hands-on session, and we will create a STEAM moving art gallery project. Hopefully by now you have received your STEAM in Practice instructions and your Blackline Master. If you haven't received these, please do let us know via the email at the end of this slide. So there are some instructions for you to follow and a Blackline Master, which you can see on the right there, that you'll need to copy onto 150 to 200 GSM cardstock. And there's just a few little instructions that we ask you to complete before the session, and this will really free up our time so that we can get creative in even more interesting ways. Hopefully that's whet your appetite, and that based upon today's learning and the learning ahead, that you really feel excited about the potential for STEAM learning in your school. If you have any questions prior to next week, please contact Alwyn with the details on screen. See you next Tuesday.
And we're lucky we've actually got Elwyn with us today. So if anybody has any questions about next week, Elwyn's there. Elwyn, did you want to add anything else to
the discussion? Yes, what we're hoping is that we provide a platform to take the participants on. So we end up with basically a starting box, basically a box, and that's what we're going to have. If that's made, we then have the potential to engage for a bit longer time with Katie in examining cultural understandings of Christmas and what we might do, and then what we might come up with. So in that one there, it didn't show up very well on the video link there, but basically what we had was an automata model, and the idea is that it provides teachers with a model that they can take away and use straight away in the classroom, and then get in the extension of problem solving and thinking about the thing, we want to try and come up with some ideas that the students will be able to make it their own. So that's basically it. And the information will be coming out at the end of this session. So no one's got it yet, I don't think, because we only had 2 more names added at 4:30, I think. So
Thanks, Elwyn. Yeah, because I've got chat box coming through saying I haven't got it, so we'll make sure that happens for you. So to close the session today, I just wanted to open up for any questions that you might have for Linda or myself. No?
I just thought of a question now. I'm just thinking, when you do Fermi questions in the classroom and you want kids to work together in groups, do you think, in my classroom, I've done a mix of both. I've done, say, mixed ability groups, but then I've also done it the other way where I've put kids in similar abilities. Do you have any opinion on what you think might work when we are dealing with Fermi questions?
In terms of structures in the classroom, yeah, it's important, I think, first of all, if they're used to having roles and responsibilities within a collaborative group, then that's certainly great. So I'm just assuming that they have. What I like to do is get kids to come together around the problem. Now, if there is a huge diversity in the group around then solving it, you might see that some people are more passive in that, but often it would be mixed ability based on interest is the way that I would go. But the active role of the teacher in that is to really watch and observe and build the confidence of kids to contribute. So it might be a lot of that close proximity prompting for the kids to engage. Because if kids go into ability groups, they already know and they label us, and we want to overcome that, because the thing with maths anxiety is a lot of people think that they can't do it. And so, we have kids now so gorgeous going, "Oh, Mrs. Leach, I just realised my thinking was really on the wrong way and now I'm going to redirect." And we go, fabulous. But we started with a box of questions that they would come and pick out, or ones that we would just put on their table first, so no one knew. And so they were levelled initially to build confidence, and then broke it up into creating and going together based on a question.
Right. Okay.
You did it.
I think you probably know your students the best, Maddie. So, the mixed ability versus the non, it really just depends on how you manage your class.
Right.
Yeah.
Right.
Yeah, because I've done it. The group that I've done it with have been a group of high ability students. So, but then what I did was mix from different schools. So I mixed up the schools. So that forced the students to talk to each other, and boy, did they talk to each other. It was really good to see what they were doing.
Right. Well, that's right. And that's what surprises me, because, you look at the kids, like you say, who can perform exercises really well, and, they get the B's and the A's, but then when you put them into these groups and you give them these, Fermi situations, it blows me away. Not all the time, but sometimes some kids who I think would be passive you know, who might not, you know, they might be the C or the D student, but they really come out with some interesting things when it comes to these Fermi questions. So that's just why I was curious, because I really see both sides of it.
It's really interesting. I mean, I've worked the last 3 years in about over 350 schools, and we were starting, the classrooms did not have any collaborative or problem-solving learning in them. So it was a real challenge, but we saw exactly that it was often the C kids who actually had the deeper understanding. A lot of the A kids have fluency and they get the right answer, but they're actually quite annoyed when you ask them to share their thinking. They go, oh, because I know. Yep. Well, you need to show me how you know. And so we had to put in a whole range of different structures in order to do that. Yeah.
Right.
There's not one right answer, I guess. But it depends on the climate and the context. We certainly moved to mixed ability from pairs.
Yeah.
Mm. Well, thank you, everyone. If there's no other questions, we'd like to thank you for your time this afternoon, and hope that you enjoy the upcoming sessions as well. And we look forward to any feedback. Again, that our emails are there.
And Tanya, the email for the next workshop should come out shortly after this one. So if you haven't got it by tomorrow, if you can contact me tomorrow.
Yeah.
Thanks.
Okay.
Lovely. Thanks, Amanda. Thanks, everybody.
Thank you.
Thank you.
Thank you very much.
Okay.
Bye.
Bye. Thank you.
I'm just typing in the addresses, so that's why I haven't changed.
No, that's okay. Just stop the